Okay, so I just realized that maybe it's a good idea to add another example to be done with maple, a slightly more complicated model, and I'll make this last part strongly recommended rather than just mandatory. I think it's useful to see an example in which the distinction between working with or without maple is much clearer, because the examples I showed so far, you can certainly save some time with maple, but at the end of the day they are not that difficult to the point where you would really suffer if you don't have a computer algebra system available to you. So I want to go over an example. This won't be an epidemic model, it will be a demographic model, but it's a type of model that I'm familiar with, because I've done quite a lot of work on this type of model. And I'll show you basically a kind of, again, simplified version of it so that we can fit it in a couple of minutes when we go over this presentation. So again, the goal of this video is to really show if you don't have a maple or something similar, not only it's more tedious, but stuff can be prone to errors quite a lot, because the expressions are no longer nice. You can't easily manipulate the terms. The terms are not obvious on how to manipulate them. Even with maple, as you'll see, you still have to use your brain. So I would say this example shows when maple is actually needed, or something similar to maple. I'm using maple to illustrate this analysis. But at the same time, why it's extremely important to still use the pencil and the paper and the brain and the judgment of what you see at all points, because there are steps or parts in the analysis in which maple actually doesn't help, and it can actually confuse you further if you don't use your brain when you should. On the other hand, it does help quite a lot when it's a matter of doing some tedious computation or manipulations. So the example I want to show is a demographic model, a so-called 2-sex model. I've done quite a lot of work on this, not just on demographic models, but on epidemic models involving 2-sex models like sexually transmitted diseases. So these are just models in which the individuals are separated by sex, right, by gender, so females and males, which means the simplest possible model will have two equations. And so I want to go over versions of the so-called logistic 2-sex model. Logistic in the sense that the mortality is made to be increasing with the population, just like in the logistic equation that you learn in this class, but in the context of 2-sex model. So actually the paper that I pulled this example from aims to actually to analyze a generalized version of the model, in which you have some generic functions for which you only assume some properties, but you don't actually take a specific form when you do the analysis. So these are the equations of the females and males. You have the so-called mating function, or the birth function, which depends on the females and males with some important hypotheses that you have to make on this function. We won't go into that right now. You have a birth function, and then you have some probabilities at birth of whether the newborn is a female or a male. Then you have the mortalities for the females and the males, again depending on the total population P. So that's like the most general, a very general format of the model. So going back to maple, I already entered here a version of it in which I actually take some specific functions or some specific forms of these functions in the model that you've seen before. Again, I don't want to get into the details on how you choose these functions. These are not completely random, the way I throw in these terms. This is just one example of the mating function, the so-called harmonic mean. I just want to point out to the meaning of the variables again so that we can follow through with our analysis. So beta, the birth rate per capita, or per pair if you want, because this is a 2-sex model. This quantity fm over f plus m will be like the mating function, and by f I will denote the probability of a female newborn. So that's very important to keep in mind, because again, maple will not know the conditions you already established on these parameters, right? So from now on, whenever you see f, you should always remember that f is between 0 and 1 because it's a probability, right? The probability of a newborn being a female, which means the corresponding quantity in the equation for the males obviously is 1 minus f. So if f is the probability of a female newborn, obviously 1 minus f will be the probability of a male newborn. Again, for simplicity, I choose the same mortality for females and males. In reality, they're not the same. And the logistic mortality is given by this increase in linear term. So f plus m is the total population. So if you look at just this parenthesis, that's essentially the mortality rate, just the death rate if you want. Again, increasing with the total population to make it logistic. And let's see, with that in mind, just like in the previous example, we follow the same script really. And in most of the papers I've done, at least, essentially this is the way I play the game, so to speak. It's still with the pencil and the paper, but I essentially have Maple to assist me in simplifying the expression. So let's find the equilibrium points first. I guess I forgot to hit enter on the equations. Let's one more time. So right off the bat, you would see that the first two equilibrium points, we can easily dismiss them, right? I mean, those are not feasible in the biological domain because they are negative. So one of them is negative, one of the values at the equilibrium point, it's negative, so these are not biologically feasible. I should say, on a side note, again, that's not the topic or the part of our class, there is an extinction equilibrium, or in other words, let me put it differently, there is a condition under which the population goes extinct, but that cannot be proved as straightforward as with the Jacobian, because the functions involved here are not defined at 0, in fact. So you have to use different techniques from analysis to prove under what conditions the population goes to 0 or not. So surprisingly, kind of the opposite of what we've seen before, the extinction equilibrium actually requires a little bit more, let's say, non-standard math, shall I say, okay, to show under what conditions the population goes extinct or not. Because 0 is not it's not basically the root of the system of the right-hand side set equal to 0. When you set equal to 0, you don't have 0, 0 as a solution because these functions are not defined at 0, 0. You can still prove that the solution may approach that point in the limit by other means, but not by linearization, not by the Jacobian method around 0, 0. So on the other hand, the positive equilibrium, in other words, the situation under which the population approaches a positive limit, so you want to know under which conditions that equilibrium is stable, in that case the Maple can solve that for you easily. As you can see here, this is the value of f, this is the value of m at the equilibrium point. Now let's talk about the feasibility a little bit, because notice right off the bat we'll have to actually use some logic or some judgment of what we know about these parameters, because Maple at this point may not be that helpful. So you could say, for example, okay, I need this to be positive and I need this to be positive for the equilibrium to exist. This is not helpful because it's possible that you put extraneous conditions. So what if I rearrange the terms a little bit? What if, just like in the previous cases, in fact, there is a simpler condition which ensures both f and m are positive. I'll have to manipulate this term somehow, and there's no obvious way to do that unless we give it some trial and error, so to speak. So what you could do at the very least, you could pick one of the values and copy it here in the math mode, and maybe try to simplify by size. I always go by simplify by size option. Just to see if I can get a better expression. I didn't see any difference in this case. Let's copy the value of m in the math mode. And then I'll simplify by size this as well. And I can actually get somewhere at this point. Now notice here is the value of f at the equilibrium point. This is the value of m at the equilibrium point. Maple won't tell you, but you should notice that there is a common factor between them. So when you talk about the sign of f and m, one thing to keep in mind is that f is between 0 and 1. So you have this minus on the out. I mean, that's how Maple chose to pull the minus out here, but don't make sure you don't lose it. Minus 1 plus f, again, Maple won't tell you, but this will be also negative. So minus here, minus f, minus 1 plus f, both are negative, which means for both f and m to be positive, you only need this parenthesis to be positive. So as it turns out, the condition, negative, I'm sorry. So as it turns out, the condition for existence of the equilibrium point is beta f squared minus beta times f plus m to be negative. And you can maybe rearrange the terms on the right hand side. So if I move everything to the right hand side, that's beta times f minus beta times f squared minus m greater than 0. And actually you can interpret this biologically. It's actually easier or better to, let me see if it looks better if I write it in the math mode. If you pull out beta f, you have f times 1 minus f minus m greater than 0. So anyway, Maple decides to flip it around again, but this will be the existence for the conditions for the existence of the equilibrium in the biological domain. In other words, the condition for a positive equilibrium point. In fact, to make it biologically meaningful, again, you can write it in the form of a reproductive number. So you can move m to the other side and divide by m, and then you can interpret this biologically just like we did it for the epidemic reproductive number. 1 over m will be the lifetime expectancy, and then you can interpret the top. It's a little bit more complicated than that, but roughly speaking, you can interpret essentially the offspring produced during the expected lifetime by a typical pair. So again, what I want to point out, what I want you guys to get out of this, those of you at least who take the summer class, is that Maple helps, obviously, because it saves me the time to actually solve the system. But then Maple is not going to help you as much to manipulate this condition and write it in a biologically meaningful format. You can still use Maple to simplify further, right? I mean, for example, going from here to here, I use Maple to simplify. But then at each step, I always have to use my judgment and notice the features that are to be noticed. In this case, the fact that the condition of positivity is the same for both f and m. And with that in mind, let's move on to the Jacobian. It's a big mess, all right? That's the Jacobian, and let's now assign the equilibrium values for both f and m. So again, I'm going to use copy and paste. Make sure you don't lose the minus. That's part of the value of f. And then I assign the corresponding value to m, going all the way up. That's the value for m. And now let's see if the Jacobian looks any better. So enter J in the math mode, highlight and simplify by size. And doesn't look any better. Actually, let me zoom out just a little bit because, okay, good, because I want to see it in the matrix form. All right, so again, Maple is needed to make some stuff out of it. It's not obvious what the sign is for each of these entries. Make sure you carefully understand which entry is, like, I mean, where does it end or where does it start? If you highlight one of them, it should clearly indicate where it stops. Sometimes it's a little bit confusing. So, for example, the first entry on the second row is what I just highlighted now. So again, Maple to the rescue. We need to find the trace and the determinant. So I'm going to highlight the matrix again, and let's start with the determinant. Not much I can tell. I'm gonna highlight it. Let's see if I'm lucky. That will have a nicer expression if, again, I use Maple to simplify it by size. And I'm lucky in the sense that Maple managed to factor this nicely. Or shall I say, it happens that the determinant can be factored, and therefore Maple could factor it for you. We still have to use our judgment. Under what conditions the determinant is positive? Well, let's not forget that minus 1 plus f again is negative, right? Because f is a fraction, it's a probability. So minus 1 plus f is negative. To have a positive determinant, we need this quantity to be negative. That's the same condition as this being positive, right? If you reverse it, this condition, I'm gonna copy it again so you could see it down here, is the same condition for which this parenthesis is negative. If you move the terms on the left, you get beta f squared minus beta f plus m negative, and this is just right. So far I don't get any new condition. The determinant is positive if the equilibrium exists. All I have to verify now is whether the trace is negative as well. So let me copy the matrix again. And let's use Maple to compute the trace. Not much I can tell. Let's see if I can simplify it again by size. And I get somewhere. But again, it could be quite confusing. And I suppose this is really the highlight of the presentation. Does this involve a new condition or not? So far, I know that I need this condition that I highlight here. I need this for stability. But the question is that all there is to it, or do I need to add this condition as well? Because I know that the trace must be negative as well. So, for example, it looks like in addition to the condition above, I need to add this condition, that 2f squared minus 2f times beta plus m is less than 0. And unless I'm using my brain very carefully so that I don't put extraneous conditions, I may not be able to realize that actually, as you will see immediately, this condition is already satisfied. But it's not at all obvious, and Maple is not going to help you. You just have to basically do some trial and error and essentially manipulate the terms. It's kind of sometimes to be expected that usually the stability is given by a single inequality. Not always, but sometimes, most of the time that happens, and this is the first thing to verify. So if I move the terms to the right hand side, this condition becomes 2 beta f minus, let's actually pull out 2 beta f, I suppose. Let me see if that's gonna help. Yeah, 2 beta f and then 1 minus f again, minus m greater than 0. Okay, so that is the condition for the trace. But remember, we already have that beta times f times 1 minus f minus m is greater than 0. Oops, I'm gonna typo here. And now if you compare the two, I hope it's pretty obvious that once this is established, then this is also satisfied. Now think about this trace condition. If I break down this 2 times beta f times 1 minus f, if I break it down into 2 pieces, I'm going to leave it like that in the, because if I hit enter, Maple will combine them again. If I break it down like that, and I know this part is positive, right? So that's the key thing, right? So the determinant condition is already included in the trace condition. So if I know already that beta f times 1 minus f minus m is positive, adding another positive quantity, because this is always positive, remember, f is between 0 and 1. So adding another positive quantity, of course, will still maintain the sign greater than 0. So the trace less than 0 is equivalent to this, which automatically follows from this condition. So as it turns out, again, the equilibrium is stable, just following a single inequality condition, which is established from the existence of the equilibrium. So I hope it's a little bit clearer on what I mean by using Maple as your assistant to do the heavy lifting, essentially. Because for the most part, you're still on your own, and that's the case in most complicated endeavors, I should say. I mean, don't expect Maple to essentially to hit the button and then give you the answer, unless, of course, you work with a program that is especially designed to solve from top to finish your problem. If the problem is new, you'll have to basically adapt yourself. So with that in mind, now for real, that's the last part for week 4 material. See you later.